lesson on electromagnetic radiation. And electron structure. So we're going to go into the atom and figure out basics of where the electron is located and what conditions, energies, and such. Electromagnetic radiation, EM, is pure energy, and pure energy has several characteristics. One is wavelength. Wavelength is measured in meters, and its symbol is lambda, Greek letter L for length for lambda. Frequency is measured in several different units. It could be hertz, which I prefer. AP exam prefers second to the -1, or 1/seconds per seconds. So those are units, and it's abbreviated by the Greek letter nu and for number. If it's pure energy with electromagnetic radiation, you have the equation C, speed of light, is equal to the lambda nu. And the speed of light is 3 times 10 to the 8th meters per second. So, sample problem, if you are given lambda be 1 times 10 to the -3 meters, calculate the wavelength. So you have 3 times 10 to the 8th equals 1 times 10 to the -3 times the frequency. Solve for the frequency. Nu equals 3 times 10 to the 11th hertz. Now we're going to go through a whole bunch of scientists and experiments. So it's a list of history of things. One of the first people that studied energy is Max Planck, or Planck. He said that energy is not continuous. In other words, energy occurred in small sections like atoms, chunks. So he said energy comes up in chunks, and this energy called one chunk is a quanta. So a quantum is many of these chunks. In his equation, the energy of these chunks is equal to n, the number of energy packets, or quanta, times a constant, which they named Planck's constant, times nu. Planck's constant is 6.616 times 10 to the -34. For the above equation, calculate the amount of energy of one of these quanta that has a wavelength of 1 times 10 to the -3 meters. So the energy is equal to 6.616 times 10 to the -34 times 3 times 10 to the 11th. That gives you 1.98 times 10 to the -22nd joules. This is an incredibly small amount of energy. The reason why energy appears to be continuous is that the chunks are so incredibly small. It takes a lot of sophistication to isolate one of these quanta. Which brings us to Einstein. Einstein won one of his Nobel prizes in physics, not for E equals mc squared. That was too controversial. What he said was he described the photoelectric effect. The photoelectric effect is how your solar calculators work. What it happens is you have a piece of metal that light shines on it with a certain frequency, and that light kicks off an electron down a wire, which is called electricity. Well, if you said light was a wave, that means that energy would be dispelled over the entire surface of the photoelectric cell. And that energy is not nearly great enough to kick out any electrons. So Einstein took Planck's idea and said instead of these things being spread out, you have a photon or a chunk of light. Photon and a quanta, same thing. All that energy now is isolated on one thing, and it hits an atom, and now it has, since it's concentrated, enough energy to kick out an electron. Experimental physicist Compton, he did the experiment that proved Einstein right. So his experiment proved Einstein to be correct. So between Planck and Einstein, they came up with the concept of wavicles, which is something I coined, wavicles. A wavicle is a wave that acts like a particle. And you can do some calculations with this. The equation is mass is equal to Planck's constant divided by lambda c, where c is the speed of light, because we're talking about waves traveling electromagnetic radiation traveling the speed of light. And for the above situation that we're going to use throughout this lesson, 6.616 times 10 to the negative 34 over 1 times 10 to the negative 3 times 3 times 10 to the negative 8. Solve that, you get the mass of one of these electron wavicles, or photon wavicles, 2.21 times 10 to the negative 39 kilograms, which is incredibly small. The next scientist in line is de Broglie. De Broglie reversed this situation. He said, well, if you can say waves are particles, can't particles be a wave? Completing the wavicle situation. And so he theorized and came up with an experiment and said that lambda, the wavelength, is equal to Planck's constant divided by the mass times the velocity. Since we're talking about particles, we can't do the speed of light here. They can approach the speed of light, but it can't be at the speed of light. If you do that for the wavelength of one of these electron particles up here, you get, putting this number in, 1 times 10, on the order of 1 times 10 to the negative 11 meters. Meters. So that's the wavelength of an electron particle wave. The people, you could do this like Star Trek transporter beams, stuff like that, but the wavelength for people would be so incredibly small, it would be undetectable. It's smaller than Planck's constant itself. Bell Labs, now we move to the situation where it's not individual scientists, but groups of scientists working in collaboration. They proved de Broglie correct. And what they did was they shined electrons through a crystal of salt and found a diffraction gradient. Diffraction gradients only occur with particles, or with waves. Particles will not show a diffraction gradient. White light, more background. White light is a mixture of all colors blending together. Roy G. Biv, all lights shine together, and this is produced when you have a lot of heat involved, and it spreads out the all sorts of motion of the particles, not just emission of electrons, but spinning, rotating, and everything else. A line spectrum occurs when you have lines of color. So if you have low energy or pure element, you'll have a separate line of color, and each line has a individual frequency, which we've shown above corresponds to a specific energy. So why, if you have a pure substance, would you have individual lines of color or specific energy? Back to scientists, Bohr. He looked at the data for hydrogen and other elements, and he explained the line spectrum by having the electrons be only in allowed orbits. He worked data, but he didn't explain why they were in allowed orbits. He just said, I don't know why, but here's the math, and it makes sense, it works. He said that the energy of one of these electrons in orbit is equal to negative 2.178 times 10 to the negative 18th z squared, z is the number of protons, over n squared, which is the orbit number, 1 being closest to the nucleus and infinity being away from it. What we're going to be concentrating on in this course is H hydrogen, where z equals 1. So his model, if you will, of the atom had the nucleus with different circular orbits surrounding that. And if you look at it, a cross section over here, n equals 1, there's a big jump to n equals 2, there's a smaller jump to n equals 3, smaller jump n equals 4, because as you go farther up, the orbits get closer and closer and closer together. N equals 5, and that's important later on when we talk about stuff. So the nucleus is down there someplace. So let's calculate the energy given off if an electron jumps from the n equals 5 to n equals 1, which is a pretty substantial jump for an electron. The change in energy is equal to the change in z squared over n squared. So this is the equation you're going to be concentrating on in homework. For the hydrogen atom, z equals 1. NF is your final, NI is your initial. If it's a negative number, that means you're going to get energy out. If it's a positive number, you're going to have to put energy in. Since the electron's falling closer to the nucleus, you're going to get energy out, so you're going to end up with a negative number. Plug in NF equals 5, or NF is 1, because it's your final. NI equals 5. Plug that math into the equation, and you get the change energy to be 4.57 times 10 to the negative 19 joules, and it's going to be a negative number. The negative number means your energy is leaving. So a photon of energy leaves. If you were going to elevate electron from n equals 1 to n equals 5, you'd have to put a photon of energy in, so that would be a positive number. Going back up to Planck's constant, or Planck's equation, you can set that equal to 6.616 times 10 to the negative 34 times the frequency. And so for the frequency is 6.9 times 10 to the positive 14 hertz, which is a high energy photon. Which brings us to the quantum mechanical model. Bohr never did explain why the electrons were in certain places. He just said, hey, the math works. Scientist named Schrödinger said, well, he combined the concepts of Einstein, Planck with Bohr and said, hey, let's not have the electron being a particle, but a standing wave. Standing wave reinforces itself, where one wavelength is equal to one radius. Then the wavelength corresponds to the circumference of the circle. And that's why the distance between the orbitals gets closer and closer as you go out, because the circumference decreases more. He developed, using quantum mechanics, a psi equation. Psi equation is the wave function. The wave function gives you the total potential energy and kinetic energy of the electron wavicle. It does not give you the location. It does not tell you the location, just the energy. Heisenberg uncertainty principle kind of walked hand in hand with this. He's studying independently uncertainty principle. Abbreviated HUP, which is much more easily to do. He says there is a limit to finding both location and momentum, which is speed, in anything, especially considering the orbital. He was talking about in general, but in our case, we're talking about the electron, so in the orbital. There is a limit, there's a fuzzy area. And the reason is, to measure something, you got to interact with it. When you interact with something like an electron, you are altering its location or its speed and or momentum, same thing. His equation is the change in x or the uncertainty in the x, times the uncertainty of the momentum. Since we're talking about one substance, the velocity is what's the variable there, has to be greater than or equal to Planck's constant divided by 4 pi, which means you cannot have a set orbit. You're going to have only a fuzzy area of that orbit where you can locate the electron. Using this idea, which reinforces Schrodinger, which says the electron is not a particle but a wave. Particles have set orbits. Waves oscillate. Schrodinger came up with a psi-squared equation, which is the probability of finding the electron. In strictest terms, if you're just graphing the probability versus radius, it looks like this. You're much more likely to find it closer to the nucleus than far away. But if you account for the volume using calculus, you get a volume consideration, probability per volume, and you get stuff like this. You get a distribution thing, and the peak of this probability per volume corresponds to n. So this would be n equals 1. If you had a different distribution with 2 wavelengths, you'd have n equals 2, etc., etc., etc. So it could be over here, it could be over here, but probability is right there. So this is the link between Bohr, which said the electron has to be exactly in this orbital, and Schrodinger, which said the electron wave is close to that thing. Putting the two ideas together, you get the nucleus, and you get the modern model with orbitals, and each orbital is greater than. You'll find the electron greater than 90% of the time inside this orbital. Could it occur here? Yes. Could it occur here? Yes. Could it occur in the nucleus? No. That concludes this lesson on electromagnetic radiation and electron structure.